Hello, we're going to start off this semester with set theory, get something basic that we'll use several times this year, especially toward the end when we talk about probability and statistics. It's a good background, so hang in there. It seems a little bit esoteric maybe, but it really is useful for some things. So let's get going. Basic set concepts. Always start with the basics. And talk about basics, it's time to turn on the pen in case I have to make a note. So, there we go. And check with the pen, see if the pen is going to do the same. And I think we're off to the races. See what we do this time. We've got 8 different objectives. Don't be turned off by that. Each one of those is relatively simple. Starting with, what is a set? You can't talk about set theory unless you know what a set is. And basically it's a collection of objects. The important thing is you know what's in the set, what's not in the set, or what's in the collection, what's not in the collection. The individual objects are called elements or members. It's just vocabulary, folks. And this is a better description than the original one. The set must be a well-defined collection of objects. What we're saying is you know what's in the set and what's not in the set. Also, you might make a special note, it doesn't make any difference what the order is for the elements of the set when you make a list of them. Usually we use capital letters like capital A, capital B, and so on. Now, there are 3 ways we describe sets. First, you can use a description, a word description. Here's an example of using a capital W to represent the days of the week. The second method is the roster method. The description method, the roster method. Now I'm going to sneak one in here that isn't shown on this particular slide, but I'm going to sneak it in here anyway because it really, I think, should have been here. And that is called the set builder notation. Three methods: a word description of a set, the roster method, just listing the members, and also the set builder notation, which we'll get to in just a little bit. So, back to the roster method. There's our capital W, represents a set. We've got an opening brace. That's a brace, not a bracket or parentheses. You've got a closed brace. Inside, you've got a list of those, and each one is separated by a comma. There are the braces. Those are the curly things. We've got some examples as we go through here so you can sort of practice as you're learning. So write a word description of the list. So what we've got here is, notice we've got a capital P, of course, and we've used the roster method to show it to you. It includes Washington, Adams, Jefferson, Madison, and Monroe. What you want to do is write a word description of that set. So how would you describe the 5 names that you just see there? Well, there's one way. The first 5 presidents of the United States. I might add that just in case there's more than one United States, you might add United States of America, just in case there's a United States of Brazil. Next, this one asks, use the roster method to describe set C. Capital C again, notice. This is the set, and here's a description of the U.S. coins with a value less than $1. I hope you can get all of these. So pause this video. You want the roster method, so your answer will start by looking like this. Capital C equals, open braces. You're going to make a list of those items, put commas between them, and put a closed set of braces at the end. Well, did you pause it? Did you try it? Come on, really? You can try it. Don't fake it and think, okay, I'll just do it in my head and decide whether I got it right or not. Sometimes we fool ourselves. So please use a pencil and paper as you're going through these videos. Now we get to set builder notation. This is the one that I said was number 3, or the third type of way of describing a set. And it's a little bit technical here, but you can get used to it right away. First of all, there's the capital letter again, capital W for week. And this is described as W, set W is, that's the equals, the set of all elements X. So we're telling the listener what we're using for a variable. We're using an X, such that, this vertical line means such that, it's just an English thing, such that, and then we have the description after the vertical line. X represents a day of the week, and then we close it out. There's that closing braces again. Set W is a set of all elements such that X is a day of the week. So here we go. We're going to change this one to roster method. So this time I want you to do it this time. So we're talking about set A. So pause the video and tell us what's inside the curly braces. Okay, come back when you're ready, when you've got it written down. Welcome back. This is what you should get. There are exactly 2 months that start with the capital letter M, March and May. You don't have to have them in that order, just so you've got them there. And it would be silly to write March down twice because you'd be wasting paper and you'd be wasting pencil. Next, the empty set. Special set, very special set. And there's 2 ways of writing the empty set. The empty set means you've got something that has nothing in it. It's like an empty bucket. One way of describing that is just use those curly braces and have nothing in the middle. Nothing between them. Another way you can describe the empty set is using the Greek letter phi. These represent exactly the same thing, the empty set. Now, here is something to watch out for because you might be tempted to do this. Take a look at this. Despite what you might think, this is not the empty set, because notice there's something between the braces, so it's not empty. So do not write this for the empty set. And down here we've got a couple of examples. Example number 1, the set of all numbers that are less than 4, and this is the key word, and greater than 10. We'll pick a number, 3. Sure, it's less than 4, but it's not also greater than 10. We'll try 15. Sure, it's greater than 10, but it's not less than 4. And means both of those parts of the sentence have to be true. None of those are true, so this is a way of describing the empty set. Sorry. My graphics tablet is a little bit on an angle here. That's better. Number 2 example. The set of all x such that x is a fawn that speaks. Well, I hope you know by this time what a fawn is, but if you don't, it's a young deer. And you know that deer don't speak, and obviously fawns don't speak either. So there are none, and so this is also an example of an empty set. So how about these? We're going to test and see whether you really can figure these out. Is this the empty set? Pause for a second, write your answer down. True or false? Is it the empty set? No. There's something in it, so it's not the empty set. How about this one? Is that the empty set? No, it's a number. It's not a set. And last of all, actually next to last perhaps, is this the empty set? The set of all x such that x is a number less than 4 or greater than 10. Well, I suspect someone, or maybe a few of you, are going to jump into there and say, oh wait, I remember, that's the empty set. Well, you made a mistake, because in that previous one that you remembered, it had an and between those two phrases. Or says, or means that this is true or the other one is true. If either one of those is true, the whole thing is true. So if you pick a number like 3, since it makes the first part true, it's true, and we don't even care about the second part. Or if you pick a 99, 99 doesn't make the first true, but it makes the second true, that's good enough because we're talking about or between those two. And last of all in this group, the set of all x such that x is a square with 3 sides. So I dare you to come to class the next time and show me a square with 3 sides. You should know the square has 4 sides. 3 sides means it's a triangle. So this is the empty set. Next, a little bit more notations. Now, just in case you're interested in the Greeks, for example, this symbol actually is a Greek letter. It is an epsilon. And the epsilon is used to say that an element or an object is an element of the set. In other words, you can find it in the set. And this one, the same epsilon but with a line through it, says that it's not an element of the set. So let's take a look at this. Is this true or false? This statement right here has element in it. So this is saying R is an element of this set. So you're looking for, is R somewhere in this list? Well, yes, because this list contains A, B, C, and we ran out of time, so we just put an ellipse in here that said, see that pattern A, B, C? Continue it until you get to the Z there. And of course, or R is somewhere in that missing part that we understand. So, that's true. Second one, 7 is not an element of the set that has 1, 2, 3, 4, and 5. And that is what? And that is true because 7 is not in that set. How about another one? Okay, this is a tricky one. It doesn't mean you can't get it right, but you need to know the definition correctly. Turns out this is false. Why is that false? Well, I can best describe to you why it's false by taking this and altering it so it becomes a true statement. So on the left, we have the set containing the letter A. And we want it to be a member of this set. Well, the set as we have it over here has an A, it has a B, but it doesn't have this set A. So what we'll do, so we can make the statement true, is we'll put the set containing A inside that new set. And now it's true. Next, the set of natural numbers, N. It's also called the set of counting numbers. And if you can go back to when you were rather young, not in kindergarten yet even, your parents wanted you to count, or not to count. And you would go 1, 2, 3, and the further you get, the more excited your parents are. Those are the counting numbers. So put N up here. We already know what that is from down there. Another set you ought to know about, and these actually build on each other. So set W is the whole numbers, and they include all those natural numbers plus one extra. So the whole numbers include 0, 1, 2, 3, and so on. Similar to the natural numbers, but it also has the 0 in it. The next one, now this is where we sort of get off the track with letters, because natural, N, whole, W. This one's Z, and it represents a set of integers. But again, we're building upon the ones we already have. So let's put these in. We've already got those from the set of whole numbers. And we've also got, for the integers, we've got the opposites of each of those numbers. Those are the integers. Don't ask me why it's Z. I don't really know. Two more to build on. The next one is called Q. And these are the rational numbers. The rational numbers. And there's so many of those, and they're so squashed together, they make up the whole number line practically, but not exactly. But they do look like this. The rational numbers look like common fractions. So this is the set of all A over B such that A and B are chosen from the integers, and one additional condition. The number in the bottom is not allowed to be 0. But you know that, right? And the last one we're going to hit is because although the rational numbers just about fill up the number line, they don't really. Now this is a historical matter, and it's a little bit esoteric, but because there's so many and it's so difficult to really explain, these are the numbers that we already have from the rationals, plus ones that fill in the gaps that you can't even see. So I'm just going to say all real numbers. And leave it at that. All real numbers. All right, let's move along. We're over halfway now. Again, we're going to say, use the roster method to describe set A. Set A is a set of natural numbers less than 5. So write your answer down, see if you get it right. Remember, the natural numbers are 1, 2, 3, 4, 5, 6, and so on. Okay, there is set A. All the natural numbers less than 5. Remember, 5 isn't less than 5, so you can't include that. Next, try this one. Set B. So I'll get you started. Which numbers are included in this set? What's in the list? They have to be natural numbers, and they have to be greater than or equal to 25. So 25 is included. Now up here, remember, 5 was not included because we just had less. We didn't have or equal. So what do you have? There's what you should have gotten. And I think this is the last one in this group. Use the roster method to describe this. You've got the set of all numbers x, such that x is a real number, a natural number, and x is even. So how would you write that down using the roster method? And if you got this, you're right on track. Good work. All right, these next two slides have to do with putting some of these ideas together. Symbols, set builder notation, and the roster method. Just for example, this first one is something you might see in a word problem. X is less than A. Remember, this symbol right here points to the smaller number. So x is less than A, or x is to the left of whatever the number A is. Set builder notation for the same thing says we've got the set of all x, such that x is a natural number. We're keeping it simple, sticking with the natural numbers. And x is less than 4. And if you give this a little bit of thought before you look over here, you'll see that this would be the same set using the roster method, listing them. On the second line, now this is similar to the last one, but notice you've got an equals in there. So we're up here, you had to leave out A, or leave out 4, and here you're going to include that number. So here's an example in set builder notation, and that translated to the roster method. Set or list number 3 down here. X is greater than A. We were talking about less than before. And there's a set builder example and the roster method. Look to it. And number 4 down here, all we're doing is changing from number 3, putting the equals in, and we get this for our set builder notation. Notice the equals in here. And there's the roster method for the example. On this second page, instead of just having those in one direction, we actually have an interval. We have a starting position and an ending position, and it tells us here whether we're including A or not, whether we're including B. On this one, since there's no equals, A is excluded. X is everything between A and B, not including either one of those. Here's an example with some actual numbers thrown in. And there's the roster part of the example. Next one, we do have the equals included, so it does include A, it does include B. There's almost the same example in set builder notation and the roster interpretation over here. And this just extends this with some adjustments in the greater than and less than symbols. All right, moving along. Example with that, we're sticking with the natural numbers to make things fairly simple at least. You want to change this to the roster method, so you're going to write it like this. Which numbers are you going to put in? Well, this says we're using natural numbers, and we only want the ones that are less than or equal to 100. So pause, write down your answer, and see you in a moment. Well, is this what you got? The natural numbers up to but not and including 100. How about this one? If you got that one right, here's one with an interval. And notice that the first part includes the 70. The second part does not include the 100. And we're talking about natural numbers, so write down your answer. Is this what you got? If you did, you're on track. Next, we're going to talk about cardinal numbers, and all that is how many numbers or things or elements or members are in that particular set. So if we talk about set A, again, remember, capital A, as we usually do. This represents how many numbers or how many things, the number of elements are in A. But it's also called the cardinal number for that set, or the cardinality. The symbol is read N of A, just like with functions, if you've ever run the functions before. Notice that if you have used the roster method, repeating elements don't add to the actual set. It's actually, you could say it's pretty silly, because why put a 17 there twice when putting it once there tells you whether 17's in or it's not. So what's the cardinal number of this one? In other words, N of A, or the cardinal number of A, or the number of elements in A. How many different elements does it have? You get a 4? Okay. Next, how about the cardinality of set B? Did you say 0? Well, it's not 0 because there was a number in there, or is a number in there. C, can you get this one? Do you have to use your fingers and toes? I hope not, but all right, so what did you get? 11. Did you accidentally say 10? Well, here's a tip for you. If you've got a long list like this and you're wondering, how can I get that without adding them one after the other, maybe using tallies or something to figure out how many there are. Here's how you can do it. If you want the number of elements in C, what you can do is take the last number, the biggest one, subtract the first number, and you have to make an adjustment. You have to add a 1 at the end. So for this one, you take 23 minus the 13 plus 1, and there's your 11. Equivalent sets. Okay, we're hitting all kinds of things about sets, but each one in itself is simple, and you have to figure out the way you can keep those separate so you don't get them mixed up. Equivalent means they contain the same number of elements. In other words, the number of elements in set A equals the number of elements in set B. Another way to do this, to figure out whether two sets are equivalent, you could line them up like this. Here's one set, here's another set, and match the elements up. Match the A with the 3, the A with the 3 possibly, E with a 4, I with a 5, or whatever way you want to. If you can match them up one for one, where every one in the first is matched up with something in the second, and vice versa, then you've got equivalent sets. It's also called one-to-one correspondence. And those are equivalent sets. Now we've got a question, if you're not careful, you might have a tricky time with it. The first one actually gives it away. It says the set of 5 countries shown. So the cardinality of A is 5 countries. You can see those countries down here. You could even put commas between them and braces on either side, and there will be your set A. Set B, read that carefully. It isn't all of this. It isn't the whole thing. It's just the part with the women. So it's the upper one because the women are that cyan color for their bars. Now, what do we have for those? Well, if we look at the ones for the women, if we go across, we've got 4.2 is one number that we're interested in. 4.5 is another one. 3.3 is another one. Remember the commas. Now notice there's a 3.3. We already put it. Why put it twice? There's no need to. It'll confuse us. 2.5. And that's all we've got. So the number of elements in set B is 4. Next, finite and infinite sets. We're getting close to the end, so hang in there. Finite sets, it means for that set, like this A, if you can write a number down that says how many elements are in the set, it's finite. Could be 0, could be 1, 2, 3, 4, any number you can count. But it has to be a number that you can write down. If you can't do that, then it's an infinite set. For example, a set of natural numbers. 1, 2, 3, 4. You can actually count those, but you can't find the number that says how many there are. I'll give you a tip. This is something that's going to come up later, but they've actually come up with something that represents how many elements are in set N. This is a little bit exotic, and I can't draw it very carefully. So for this character, I'm going to just make sort of an exotic looking N. This is an N that's very fancy. And if we put a 0 down here, that represents how many natural numbers there are. It's infinite, but this represents that infinite number. And this particular symbol is called Aleph Null. Aleph is, if I remember right, a Hebrew letter, and null is there because this 0 represents null characters, or null elements, or null members. And equality of sets. Very simplest. Sets are equal if they have the same things in them. They have the same elements, the same members. So you can match them up, and everything in the first set is in the second, and vice versa. Here's a check to see whether you understand this. Are these two sets equal? Okay, have you decided? Yes, they're equal. Even though they're in a different order, but remember, order doesn't matter. It's whether the elements are there or not is the only thing that matters. How about this one? Are these equal sets? Got your answer? False. The second set has 0 in it, the first one doesn't, so they're not equal. Now, you've had a chance to see some things about section 2.1. You can read it in the book. You can look at the slides if you like and start on your assignment. Now notice that if you're watching this on Sunday night and it's a little bit late already, you probably won't. But when you do, it's not due on Monday. But if you do see this in time, notice it's not due on Monday. Monday is the 22nd. It's due on Wednesday. But you should be working on those problems. All right, that's it for section 2.1. A little bit of trivia. This is the 4th time I've given this lecture this weekend and tried to record it. It hasn't been fun. I'm glad you didn't have to watch it as many times as I had to record it. You take care of yourself, and we'll see you tomorrow morning.